in remote voting systems, most recently in Argentina, New South Wales, Australia, the iVote system in Estonia, Washington, D.C., where I live, and Norway no longer pursues internet voting, though it was among the earlier ones to start. And there are many open problems. I have been working on secure voting systems since 2003. As mentioned, I have actually worked in constructive solutions, so I have been part of a team that designed voting systems that were deployed in the municipal elections of the city of Takoma Park, which is near Washington, D.C. So I have been involved in the constructive side, and as being a scientist and an engineer involved in the constructive side, I say that there are many open problems in internet voting, and it's not clear if they are solvable. So I hope that during this talk, I will be able to give you an outline of what we can do and what we cannot do. And in particular, we do have solutions for supervised voting. And so, for example, the election in Takoma Park were supervised voting, except there was a small number of votes that were cast remotely, but those were also paper ballot returns in addition to using the internet. So they relied on the paper ballot count. So let's sort of take a sense of what would we do for more secure systems. So, if a system actually, for example, the iVote system, which was recently deployed in Australia, distinct from the vVote system, which was also deployed in Australia recently. The iVote system, which was an internet voting system, actually, the problems were found during the election. So some votes had already been, tens of thousands of votes had already been cast when they found a vulnerability. And that vulnerability could have changed many votes. And there were margins that were smaller than the number of votes that were cast. So, we don't want that kind of thing to happen. Whatever, people will say the chances are high, the chances are low, whatever they are. The issue of something like this happening can create considerable problems, especially as we said, in a country like India, where even 0.5% of the votes is 2.5 million votes. So what would we do to design more secure systems? Can we test them more exhaustively? Let's test the servers better. Let's test the clients more. Let's make sure they're tested. Let's look at the code. Let's formally verify the code. Let's do this. Let's do this. You can keep on doing that. But there are results in computer science, fundamental results, that tell us that a large piece of code cannot be verified for every input. The output of a large piece of code is not verifiable for every input. So what you can do is you can find problems, but you can never say there are none, right? So you look. That's what exhaustive testing does for you, and I'm not saying you shouldn't do it, but you can't rely on it because there might be errors that you didn't find. So additionally, what happens is if we do test something, so for example, you have the EVM and it's tested and it's hardware that cannot be reprogrammed, so once it's tested, that's good, it's not going to be changed. But then as Professor Shani said, that somebody might claim that the chip was replaced. And so you don't know whether what you tested is what you use, in particular because the voter is not able to check at the time that they're casting the vote. They don't have the ability, the technical capability to check, nor do they have the equipment they might need to check. So they don't know that what you tested is really what is being used. So there's an additional requirement for voting systems. And that is, a good voting system will provide evidence to the voters that this election outcome is correct. And you can think of the voter verified paper audit trail as being that for the EVMs. This is evidence that the EVM is providing that says to you that this outcome was correct. Now notice, just because today's outcome was correct doesn't mean tomorrow's will be correct. But all you care about is the ability to check every election. You have the ability to check it. You may not be able to guarantee that tomorrow's election will be correct because who knows what can happen. But this paper audit trail actually gives you the ability to say, yes, this election outcome was correct. Now, additionally, you want this good voting system to provide evidence that convinces those who voted for the person who lost that that person really did lose, right? So you don't want the winners to say, yes, we won, because they obviously believe the voting system, they won. But there are numerous losers and people who voted for them. And you want all of them to finally go along with the election outcome and be able to say, yes, the election outcome is correct. So to the extent that, of course, there are issues of trust and there are other human issues and so on, all of which cannot be solved by technology. But to the extent that a technical system can provide this kind of evidence, you would want the system to provide it. So this is today considered a gold standard for voting systems. We are able to achieve this using procedures and paper and technology in a supervised setting. We are not able to achieve this in an unsupervised setting. Why is this difficult? Well, there's a two-pronged problem. The evidence must prove that the tally is correct, but it should not reveal the votes. So it's supposed to convince you, some observer, that the tally is correct, without actually showing you any of the votes. Additionally, you also want to address this issue of vote buying and vote selling, and you have the mafia threatening, your boss threatens you if you don't vote for so-and-so, I'll break your leg. You have all these models, and this is all known as voter coercion. Technical term, we call it coercion, though there's a little bit of bribing and so on also. And you also want that to not happen. So there are a lot of really stringent qualities, and this happens to be among the harder cryptographic protocols to design securely. Now note here, the adversary. So when you do a security analysis of a system, you model the adversary. So you say which parts of the system are not trusted. So it's not just a reliability analysis of the system. It's not just if there's an error, if something goes wrong, if there's an error, how would you fix it? And then you say, well, errors won't happen because it's robust. But we're not saying that. We are saying some intentional effort to modify the election. And intentional efforts will always chase the least secure link. So you cannot say this least secure link is less possible, because that's where your adversary is going to go. They're not going to go after the parts that you secured. So you want this to be true when the adversary can be anywhere, in the client, in the server, in the network, an election insider, and etc. Now this already sounds like magic, and you're already saying, well, we can't do this, so why try to do it? But there are cryptographic protocols that enable this. They have a couple of other assumptions which are reasonable and which can be made to happen. And I will describe that approach. And then there was this question. So the world is banking online, right? Not just the world, right? Using Aadhaar cards and stuff like that, there are proposals for rural voters to bank online using cell phones, right? So instead of an ATM, you have a shopkeeper with a cell phone, and he's going to do the transactions on his cell phone. So if we can do that, then why can't we vote online? Well, so the two problems are different in this way. So look at this, there's on the left-hand side, there's a hypothetical bank statement, and we can think about my bank holds the authentic record of my bank statement. If there's a problem in there, I can challenge it. Most countries, there will be a procedure for challenging it, especially if it's done online. For example, here I've had my own checks returned because my signature doesn't match what's on file. So there are ways to challenge transactions, and you can point to them. So you point to a transaction and it bears metadata, it bears all kinds of information about the transaction, when, where, what time, by whom, and so on. And then you can go ahead and challenge that. And most countries have protection for online transactions, more protection than they have for physical ones, because those are the ones where more fraud can happen. And essentially all over the world, banks say that they deal with a lot of online fraud. On the other hand, look at the authentic vote collection, which would be held by the election authority. And let's say that that's the collection, that's what's going to be counted. And as Professor Shahani mentioned, the challenge is in getting the vote from the voter to that collection, and then also in ensuring that the collection is counted correctly. But what I'm trying to say here is, supposing that transaction was wrong, I can point to it and I can go and say this transaction is wrong. But if my vote was changed in this anonymous collection, I don't even know it. So there's a list of votes. I don't know which one is my vote, whether it was changed or not. I'm not supposed to know. I shouldn't be able to point to it. Because if I can point to it, I can sell my vote. If I can point to it and tell that fellow that, look, I voted for this, give me 10 saris, that should happen, right? So this thing is an anonymous ledger, and I cannot identify what my vote is, and I cannot say it has been changed. So this is the difference between the two problems, and it's a big difference. And so that's where cryptographic voting systems come in. They try to combine accountability and anonymity, or verifiability and anonymity. So in a cryptographic